Howdy! This is your friendly neighborhood physics teacher here, and I'm here to review you for Unit 3 for your fall final. So Unit 3 was 1D motion. So if you look at your review, we're going to scroll up to the top again, and we're going to talk about the main variables that you need for this unit. The next one we need is displacement. So displacement is a delta x. Displacement is measured in meters, and it is a vector. Now, we've already talked about it in the video before, but just a refresher, d stands for distance. It's measured, but it's measured in meters, but it's a scalar. And that's just if you're doing generic distance. You can be more specific and say distance in the x or distance in the y. Again, those are both measured in meters, and they are both scalar. You can make displacement a little bit more specific, and it's just displacement in the y. Delta x is displacement in the x direction. Delta y is displacement in the y direction, and that is a vector. It's pretty much the same thing. They're the same thing. Just like how these are the same. Just different directions. The next thing we need to talk about is speed. Speed is represented by an S. Speed is measured in meters per second, and speed is a scalar. Remember, the scalar means direction does not matter. We just care about the magnitude. On the opposite side, we have velocity. Our velocity, measured in meters per second, but it is a vector. Speed is just magnitude. Velocity is a vector. You can be more specific and say velocity in the initial direction. You just put a little sub I. It's still measured in meters per second, and it is still a vector. And you can do velocity final. Just has a little sub f, and it's still measured in meters per second, and it's still a vector. And we have acceleration. A is represented by acceleration. It is in meters per second squared, and acceleration is a vector. We can get a little bit more specific and have acceleration in the y direction, or acceleration due to gravity. It's still measured in meters per second, but remember it is a constant, so it has a number, because on Earth it's 9.8 meters per second squared. It has a direction, because it's negative, and it's a vector. So that is the main types of different ones we're going to use. Oh, there is one more. I forgot about time. Oh no. So time is represented with a T. It's measured in seconds, and it is a scalar. So there we go. That should be all we use if we're needing to do the guess method for these. These are all the variables that we should be using. So if we scroll down to Unit 3 in our review, first question is, when you travel 50 kilometers to the east and then 20 kilometers to the west, what is your total distance you traveled? So distance, key thing is distance is a scalar. So since distance is a scalar, direction does not matter. So for distance, it does not matter. For total distance, you just take d1 plus d2 plus d3, and you just keep going. So for our total distance, we have 50 kilometers plus 20 kilometers. So we would get 70 kilometers. If you wanted to, we don't like kilometers, right? Remember from our unit 1. We don't like kilometers. We like meters. So we would need to convert that. Kilometers is in 3. Meters is 0. So we get a positive 3. So we just get, so that basically equals 70 times 10 to the third meters. That's not in scientific notation because it has to be only one number. Move the decimal over 1, and we get 7.0 times 10 to the 4 because we move it over 1, so we add 1 meters. Dun-dun-dun-dun, and that is our answer. Next one asks, what is your displacement from question 1? Your displacement from question 1. Displacement, if you look at your equations, you have final minus initial. Final minus initial. And now these is, when you're doing this equation, this is talking about position. Final position minus initial position. So knowing position, you kind of have to draw it out. So we're saying we're starting at, so we're kind of starting at ground zero. It says that we went 50 kilometers to the east. So think about like that's being mile marker 50. And then we went 20 west. So we moved 20 kilometers west. So what mile marker would we end up at? We started at 0, we went to 50, but we had to go back 20. So the mile marker you would be at is 30 kilometers. Because this would be our initial position. This would be our final position. Now, how I got 30 kilometers is 50 is positive, 20 is negative, because it's going to the left or going west. 50 minus 20 gives you 30. So now we can do our final position, which is 30. Our initial position is 0. And we get that our displacement is 30 kilometers. And again, we can convert that. You would do the exact same little method up there. But that is our displacement. I think a lot of people that get messed up on the displacement problem is they forget that this is position. So you can't always just do 50 and 20 and subtract, because you might not have started at the 0 position, and we'll see a problem like that later on. For number 3, it says, when a car moves 50 kilometers in 2 hours, what is the average speed? So let's do our guess method. So givens, it's giving us 50 kilometers. So 50 kilometers, that's going to be our distance. 50 kilometers. And it's saying it's in 2 hours. So that is our time. Do we like kilometers? No, we do not. So we gotta convert. So kilometers is 3, meters is 0. So it's 3, so we get to move it 1, 2, 3 times. So our answer is 1, 2, 3 times. That many meters. We don't like hours, so we need to convert. We like seconds. So hours gets shunned to the bottom, seconds gets put on top. So for 1 hour is 3,600 seconds. Hours cancel. So you just multiply. So you put that in your calculator, 2 times 3,600, and you get 7,200 seconds. So we have our distance, We have our time, our unknown, we're looking for speed. Our equation, you look at your equations, you'll get speed equals distance divided by time. So substitute solve. So speed equals 5,000 divided by 7,200. You get an answer of 0.69. That is now meters per second. Woohoo! There we go. So our next question, for number 4. In coming to a stop, a car leaves skid marks 80 meters long on the highway. Assuming a deceleration of 7 meters per second squared, estimate the velocity of the car just before braking. So let's do the guess method. So our givens are, one of them is stop. Stop is a given. What does stop give you? Stop gives you your final velocity. Because think about it, if you've stopped, you're coming to a stop, you're not moving. So therefore your velocity has to be 0. And it's saying that it comes to a stop, so your final velocity would have to be 0. And then it gives you your acceleration. So your acceleration. Now deceleration means it's a negative 7 meters per second squared, because it's accelerating in a negative fashion. Estimate the velocity of the car before braking. So we're wanting to know the velocity of the car before braking. So we're given final velocity, we're given acceleration. And oops, I forgot a given. And we're given displacement. We're given displacement. It says that the skid marks are 80 meters long. So let's do our unknown. What are we looking for? We're looking for initial velocity, because it says estimate the velocity of the car just before braking. So we're looking for initial velocity. If we look at our equations, so scroll up to the top of your review, and look for your equations. We need an equation that has final velocity. We need an equation that has acceleration. We need an equation that has displacement. And we need an equation that has initial velocity. If we look at our equations, the only one that has all of those is VF squared equals VI squared plus 2A delta X. So that's what we have our equation. Now we can plug in. We have final velocity. It's 0 squared. We don't have initial velocity. That's what we're looking for. We have acceleration. It's -7. And we have our displacement is 80. So let's go ahead and multiply the 2 times -7 times 80. And you get a -1,120. V squared and 0 squared just gives you 0. So we need the V squared by itself. So we're going ahead and move this number onto the other side. So you get V initial squared equals 1,120. To get rid of the squared, the opposite of squared is square root. What you do to one side, you have to do the other. So you're going to square root your answer. And you get 33.47 meters per second. So there we go. So that's how we solve for that. The key thing is to pulling your givens. So don't forget to get your givens. On Schoology, you can actually highlight on your computer. So maybe if you're having trouble finding your givens, highlight your given, highlight your number, highlight your unit. That's why I sit there and took the beginning and went over your units, because those will help you. If you can remember that, those will help you. I believe on Schoology there is a Quizlet going over at least this unit's variables. So let's go to question 5. Ashley's car breaks down and she must push it to the side of the road. It starts from rest and accelerates at a constant rate of 0.25 meters per second squared. What is the velocity of the car after it travels for 3.26 minutes? So again, we're going to write down our givens. So we have our givens. Rest. Rest is a given. And it says it starts from rest. Actually, that's a key thing there. Starts from rest. That whole entire thing's a given. That is telling you your initial velocity, because it starts, initial, rest gives you 0. So it's saying your initial velocity is 0. And it says it accelerates, so that's A, and it accelerates at a rate of 0.25 meters per second squared. What is the velocity of the car after it travels for 3.26 minutes? So your T, and it's saying it's 3.26 minutes. Do we like minutes? No. So we got to convert. We don't like minutes. Minutes goes to the bottom. We want seconds. So for 1 minute gives us 60 seconds. So you just have to multiply across the top, because our minutes cancel. So you do 3.26 times 60. It's 195.6 seconds. So that is we've now converted our seconds. And it's asking for what is the velocity of the car after. So our unknown, we're looking for a final velocity. So equations. We scroll up, look at all the equations on your review. We need an equation that has initial velocity, acceleration, time, and final velocity. If you look at your equations, you get final velocity equals initial velocity plus a t. We're looking for final velocity, so that just stays there. Initial velocity is 0. Acceleration is 0.25. And your time is 195.6. So now you just have to multiply. And you get the velocity is 48.9 meters per second. There we go. Our next question states a world-class sprinter can burst out of the blocks to essentially top speed of about 11.5 meters per second in the first 15 meters of the race. What is the average acceleration of the sprinter, and how long does it take her to reach that speed? So we're doing givens. Let's pull out our givens. So it gives us the, so it says that can burst out of velocity, essentially top speed. So bursting out, so that's our initial velocity of 11.5. And it, in the first, it says it can reach there the first 5 seconds. So our initial velocity would be 0. See, this is why it helps read the whole entire problem. The reason our initial velocity is 0, because think about it, right before you start a race, you're not moving. And it says in the first 15 meters, you can get up to 11.5 meters per second. If you look at it, it says in the first 15 meters per second. So our displacement is 15 meters. We're looking for acceleration. So that becomes our unknown is our acceleration. If you look at our equations, go to the top, scroll to the top, you can look at your equations. And you'll see that, again, we're using the VF squared equals VI squared plus 2A delta X. We have final velocity. We have initial velocity. We're looking for acceleration. And we have our delta X. So let's go ahead and do 11.5 squared. You get 132.25. 0 squared is still 0. And when you're multiplying, it doesn't matter what order you do it. So you can go ahead and multiply 2 times 15 and get 30 times acceleration. So you can maneuver this around. You don't have to go straight in order. Multiplying, remember your PEMDAS, it doesn't matter what order you multiply or divide as long as you do it in that little area. So that 0 just goes away, so you're left with 132.25 equals 30 times acceleration. The opposite of multiply is divide. What you do to one side, you got to do the other. So then you just divide your answer. And you get 4.41 meters per second squared. And there we go. Next one. A car travels at 90 kilometers per hour, strikes a tree. The front end of the car compresses, and the driver comes to rest after traveling 0.8 meters. What was the average acceleration of the driver during the collision? So it's very similar to the setup. This one is extremely similar to the other ones we've done. So we're pulling out our givens. Our given, we have the car is traveling at, so that's our initial velocity at 90 kilometers per hour. Do we like 90 kilometers per hour? We do not. So go ahead and remember per means divide per hour. So that's basically saying for 90 kilometers, you can it takes you 1 hour to travel 90 kilometers. And let's focus on each one. We don't like kilometers. Kilometers goes to the bottom. We want meters. So for 1 kilometer, there's 1,000 meters. So now we can focus in on our hours. Hours are on bottom. To cancel it, it's got to go on top. We want seconds. So for 1 hour, 60 seconds. The hours cancel. So now you multiply across the top. 90 times 1,000. And divide that by 60, because 1 times 1 times 60 gives you 60. And that is meters per second. And that gives you a velocity of 1,500 meters per second. So that is our initial velocity. And then, so the front end of the car compresses, so it strikes a tree. So what's your velocity after you hit a tree? 0. And it says that your body still moves about at a rate, or still moves for 0.8 meters, and it's looking for what rate does it take you to slow down. So what is your acceleration? So we're going to use the exact same equation we have been using. So your v squared equals vi squared plus 2a delta x. Final is 0. Initial was that really big number. Plus 2, we're looking for a delta x. 0 squared is just 0. 1,500 squared is this big number. Make sure I get all the zeros. 1, 2, 3, 4. 1, 2, 3, 4. Again, you can do you can multiply in any order. Times a. Now you cannot add those because of this a. You cannot add them because of this a. You can't do that. No. Bad. Don't do that. So I have to bring this over here. What we do to one side, We got to do the other. And that equals that. We want a by itself, so you go ahead and divide. You plug that into your handy-dandy calculator. And you get this number here. And that's your acceleration. So that's really hard. So slamming the trees will not feel good to you because you're stopping very abruptly. So that's why bones and everything get broken, because of that's you're stopping at that rate. So that's why running into something is dangerous. So next one says the slope of a position time graph represents. So a position time graph. So if we're thinking rise over run, so rise is x over run. That equals your velocity. So therefore your slope equals velocity for a position time graph. Now it's asking for what is the slope of a velocity time graph. So again, we have a graph, and it's a velocity time graph. Rise over run. So our rise is v over t, and that equals acceleration. So therefore, our slope of a velocity time graph is acceleration. What is acceleration? So what is acceleration? Acceleration is the change velocity over time. That's basically what acceleration is. It's the change of velocity over time. If you don't have a change of velocity, you don't have acceleration. If you don't have a change of velocity, you don't have acceleration. If a car moves from rest at 5 meters per second in 5 seconds, what is the average acceleration? So again, let's do our givens. So it's asking for if a car moves from rest, so our initial velocity is 0, and then it goes to, so our final velocity is 5 meters per second. It says it does that in 5 seconds. It wants to know what our acceleration is. That is our unknown. Our equation, if you look again, scroll up, look at your equations. You need an equation that has initial, final, time, and acceleration. And you look, you'll see it is this equation. So we have final, it's 5. Initial is 0. We're looking for acceleration. Time is 5. 0 just kind of goes away. You do to one side, you do the other, you want a by itself. So your acceleration is just 1 meters per second squared. The next one, if a car accelerates from 5 meters per second to 25 meters per second in 10 seconds, how far will it travel? So again, let's look at our givens. So we're given initial velocity of 5 meters per second. We're given final velocity of 25 meters per second. And our time is 10 seconds. What is the skipping around. It's asking for how far. So our unknown is how far. So we're looking for our displacement. If we look at our equations, we need an equation that has initial, final, time, and displacement. You see our displacement equals 1/2 VI plus VF T. So we can just plug in 1/2 VI was 5, VF is 25, T is 10. Remember, you have to do parentheses first because of PEMDAS. So 5 plus 25 will give you 30. And then it doesn't matter what order you multiply in. So you just do 30 times 2 divided by 2, or 1/2 times 30 times 10. Doesn't matter what order you do it in, and you will always get 150 meters as your answer. So 14. What is the displacement of the car whose initial velocity is 5 and the acceleration is 2 for 10 seconds? So let's do, again, givens. So we have initial velocity, it flat out tells you, is 5 meters per second. It says it accelerates for 2 meters per second squared. And our time is 10 seconds. And we're looking for the displacement. And we're looking for the displacement. So you look at your equations. We need initial, acceleration, time, and delta x. There's only one equation there that doesn't have final velocity. And it's your delta x equals VIT plus 1/2 AT squared. So you're looking for your delta x. Your initial velocity is 5. Your time is 10. Your acceleration is 2. Your time is 10. Do not forget the squared. You have to do it little chunks. You have to do 5 times 10 first, and you get 50. And then make sure you squared. Once you squared, you can go ahead and multiply by 2. Divide by 2, you realize those cancel out. So you're just left with 100. Then you can just add. And you get your answer. Next one, it says, what is the final velocity of the car at acceleration 10 meters per second from rest and travels 180 meters? So again, we're doing a given. So on our givens, we're accelerating at 10 meters per second squared. We're starting from rest, so it's our initial is meters per second. And we're traveling, so our delta x is 180 meters. And our unknown, it flat out asks for what is our final velocity. So again, we're going to go back to final velocity squared equals initial velocity squared plus 2a delta x. We're looking for final velocity. Our initial velocity is squared. Our acceleration is 10. And our displacement is 180. 0 squared is just 0, so that can go away. Then you can just do 2 times 10 times 180. And it gives you 3,600. To get rid of the squared, you have to square root. What you do to one side, you have to do the other. So you square root 3,600. And you get 60 meters per second. Woohoo! Next one. What is the velocity? What is the velocity of the ball that's thrown up? And it takes 5 seconds to reach max height. So it's givens. So the given itself is pretty much time. So time, it takes 5 seconds to reach max height. Now remember, when a ball throws up, you're in the y direction. You're in the y direction. Anytime you're moving in the y direction, you have acceleration. And your acceleration is negative because it's pulling you down. Acceleration is negative because it's pulling it down. So it's asking for what is the velocity after 5 seconds to reach max height. Another thing to think about is, okay, what I want you to do is I want you to throw your pencil up in the air real quick. So throw it up, watch it, now catch it. Oh, see, you missed it. Told you to catch it. That's okay. Pick it up. Let's try that again. Throw it up. Okay, at the very top, what's happening? It's having to slow down and stop. So as it's going up, it's slowing down. So at the very, very tippy top, velocity is 0. And then as it's coming back down, it's speeding up. The reason it's slowing down is because of this gravity. It's getting too far away from the Earth. The Earth is a very jealous thing. It wants everything touching it. It's like, no, wait, that's my pencil. Come back. So it's trying to get the pencil to come back to it. So at the very top, it has that split second of, I'm free, but it's because it's not moving. But yeah, gravity always wins, and it comes pulling back down. So your final velocity is going to be 0 in this case, because it's asking for a max height. And your velocity is always 0, at max height when you're throwing something straight up. So you have, in theory, if you're reading that, you're freaking out because it only gave you one number. But in dealing with motion in the y direction, there's 2 hidden givens. 0 at max height, and then your acceleration due to gravity. So our unknown, and it's asking for what is the velocity. So she wanted to know what the velocity she threw it at. So we're looking for initial velocity. So we're looking at our equations. Which one has time, acceleration, final velocity, initial velocity? It's this little handy-dandy equation. We have final velocity. It's 0. Whoops. I'll put a 0 instead of erase. That should be a question mark. We're looking for initial velocity, so that stays there. Our acceleration is negative 9.8. And our time is 5. So now we can go ahead and multiply that. 9.8 times 5, so you get a negative 49. And we need your initial velocity to be by itself. So the opposite of add is the opposite of subtract is add. If I talk, and so you get your initial velocity is a positive 40 meters per second. Man, she can throw pretty hard. Good job being softball. So now it's asking what is the max height she can throw it at. What is max height? So let's look at our givens again. So we have time, it's 5 seconds. We have acceleration, negative 9.8. We know that our final velocity is 0, but now we just figured out our initial velocity is 49 meters per second. So we gained another given. And our unknown is we're looking for our max height. Honestly, we can use any equation that has delta x in it. I think the one that'd be easier to use would be the delta x equals 1/2 VF plus VIT. Just because the other ones have to do like squaring and all that fun stuff. So I think this would be easier mathematically. Your final is 0. Your initial is 49. And your time is 5. Plus 0 plus anything gives you the same number. Now you can just multiply across. And you get 122.5 meters. And that is your answer. So now it says we're getting into graphs. We talked a little bit about graphs, so now we're getting into a little bit more graphs. So 18 says draw a position time graph, velocity time graph, and acceleration time graph of each of the following. So we're just going to go across like this. So this is a position time graph. This is a velocity time graph. And this is going to be our acceleration time graph. So the first one says person walking north at constant velocity or constant speed. So we know our velocity is going to be a straight line because it's constant. That means our velocity is not changing. There is no change of velocity. Another thing that should be dinging right now, if there's no change of velocity, you know your acceleration is 0. So you know your acceleration is 0. Because what's the definition of acceleration? A change in velocity. And so it just said that your velocity is constant, so you know your acceleration is 0. So that should be your acceleration graph. And now it's saying it's walking in a north direction. So north is a positive direction. So you should be walking up. Straight line diagonal up. It's constant. Your slope is constant. You're going up. So since your slope is constant and it's positive, there we go. So if you notice, there is a pattern. It went diagonal, horizontal, 0. Hopefully throughout this, you'll be able to see there is a pattern. But the key word there was constant. Oops. So now we have 3 more graphs. And the next one, it says standing still. So standing still. That means your position is not changing. So your position is not changing. So you're not moving. So if you're not moving, you can have no velocity. If you have no velocity, you have no acceleration. So that was a pretty easy one. Next one. You have position, you have velocity, and you have acceleration. So position for a person walking south and then back home. So you're starting at home. Okay, so you're walking south. Remember, going down the graph is negative. So you're walking south. Whoops, I want to do a different color. So you're walking south. Then it says you're walking back home. So something like that. Now, it didn't say constant rate, so I just assumed constant rate. So it could, if it wasn't a constant rate, it could look something like that. So you are slowing down, and then you're speeding back up. So wherever you're going, you didn't want to, and then you sped back home. Or, give me another color. Or you could have had something, something like that. I mean, there's all kinds, this one was so vague, there's all kinds of different ones that could be happening. Let's go back to the orange. So if it's a constant, so you have a negative slope and then a positive slope. Negative slope, positive slope. But 0 acceleration because your velocity is constant. This is velocity time, acceleration time. Now for the purple one, so as you said, this is you're going from vertical to horizontal, so you're slowing down and then you're speeding back up. So you're slowing down in the negative direction, so you're going to the 0 line or the timeline, and then you're speeding back up in the positive direction. So it's just a straight line, kind of like that. And then that is a positive slope, so that is a positive acceleration all the way across. For the blue one, you are speeding up in the negative, so you'll be going away from the timeline, and then you're slowing down in the positive, so then you're doing something like that. So that is both a negative slope, so you're doing something like that. So just giving you an idea on graphing. The next one says person accelerating northward. Person accelerating northward. So for a position time graph, go ahead and write down velocity time graph, acceleration time graph, time. So for an accelerating northward, so that's a positive accelerating. So you want to start out horizontal and get vertical. That shows how you're speeding up. You see that curve there that you're speeding up. When you get to velocity, you're speeding up. Your number is changing. And it's in the positive, so you're up on the upper quadrant, and you're showing that the numbers are getting bigger. That's a positive slope, so you'd have a positive acceleration. Now the next one, it says a person that's accelerating southward. So again, you want to start out horizontal and get vertical. So it shows that you're speeding up, but you're starting up here so you can head south. So slowing down to speeding up, like going slow, speeding up, horizontal to vertical. And that is a negative slope. So you're speeding up in the negative fashion. So it kind of looks like that, just like a mirror image of each other. And that is a negative slope, so it's down here. So the purple is accelerating in a positive fashion. Green is negative. Purple is positive. So now it's saying person accelerating, person negative acceleration in the north, and person negative acceleration in the south. So we have a position time graph, a velocity time graph, and an acceleration time graph. So person negative accelerating north. So that'd be a slowing down in the north direction. So you would start vertical and go horizontal. So you would start vertical and go horizontal. So you're slowing down in the positive direction. That's a negative slope. So you're down there. So that's negative. And then let's do a different color. Let's do pink. So then your negative acceleration south, that's actually the green one I did. So I'm going back to accelerating in the south. So that's when you're heading downward, and you start out fast and you slow down. Again, you start vertical and slow down. That would cause you're in the negative and you're slowing down. That's a positive acceleration. So your purple and pink are positive accelerations. Your green and blue are negative accelerations. On 19, it says, what is happening in the graph? So just kind of describing what's happening in the graph. I'm going to draw a very rough sketch of the graph so I can have something to go off of, but it's going to be extremely rough. So we have that. We're doing that. We're doing that. Doing that. Doing that. That. There we go. And we're not going to worry about numbers. We're just going to talk about what's happening. So all we're going to do is we're just going to talk about what's happening. So right here, where it's yellow, our velocity, so it's not moving. The reason I know it's not moving, because this is a velocity time graph. So if there's no velocity, I know you're not moving. Next thing is right here. So there, you are slowing down, speeding up, because your numbers are getting bigger. So you're speeding up in a negative direction. So you're speeding up in a negative direction. That means you're going west, down, south, left. You're going all backwards. You're going in a negative direction. Here, right here, you're slowing down in a negative direction. So you're still going in the same direction. You were not moving, so you started speeding up, then you started slowing down. So all of this, you are still moving in the same direction. So same direction. You're still moving the same direction. You've just sped up and then slowed down. Come on. Right here, that spot right there, you have turned around. You have turned around. So you were going in the negative direction. So you were going left. Now you've turned around. Now you're going right. So you physically turned around. So at this point, right here, you are speeding up in the positive direction. You're speeding up in a positive direction. Right here, you are moving at constant velocity. So you're still moving. You're just moving at a constant velocity in the positive direction. Here, you are slowing down in the positive direction. So again, this whole entire thing right here is in the same direction. You're passing the 0 line. So guess what you're doing? You're turning around. So you've turned around. Again, you are speeding up. Come on. Thing is not one to work. So again, you're speeding up in the negative direction. Here and here. You would be slowing down in the negative direction. Right here. Come on. You're at constant velocity, just in the negative direction. So hopefully that kind of helped, broke down everything. And again, all of these are moving in the same direction. So hopefully that helped kind of break down understanding what's happening in a velocity time graph. Next one, we're dealing with frame of reference. So the first thing it's talking about, your observer is a person, and this person is not moving, so your velocity is 0. And then you have a boat, so a person standing by a river. So standing by a river, your river is going this way at 5 meters per second. And you have a boat on said river that is a motor. As a motor, my motor sound effects. It's going this way at 12 meters per second. To the person, how fast is that boat actually going? Now remember, we had a little chart here. So we had observer not moving. So observer was not moving. It was the same direction. You added. If it was opposite direction, you subtracted. So our observer is not moving, so therefore you subtract. It'll be 12 minus 5. Actually, in this case, it'll be negative 12 plus 5, because 12 is going to the left, 5 is going to the right. And so you get a negative number, so it just tells you it's going to the left, a negative 7. So that boat is going at a negative 7, and the direction would be left, or in this case, west. Now, we have the observer is a person again, and we have the car. So on a little sombrero with wheels, we have a car that's traveling east at 32. So our observer is not moving, but we only have one vector to deal with. So we don't have multiple vectors. So our car to the person, our car is just moving at 32. There's no special. So if you only have one vector, it's just that vector. Now, if you have two vectors, you have to take both vectors into consideration. And the next one, our observer is the car and the person. The car and the person. So to the car, the person is also moving at 32. It's just in the opposite direction. Since the car is moving to the east, it seems like the person is moving to the west because they're passing the person. They're moving past the person. Looks to the car, the person is going further and further away from them, the opposite direction. Again, only one vector, no math needed. Just you have to think about if the object is if the observer is moving and the object's not, the direction is flipped. So now we have the plane. So we're going up in the sky. So we have the plane and the bird. So the plane is going at 125 meters per second, and the bird is going at 17. So we're going to go back to our little chart here. This chart's a little bit different because now the observer is moving. So the observer is moving. So if they're going in the same direction, you would subtract. If they're going in the opposite direction, you would add. So in this case, you'd be going in the opposite direction. So you just add your two vectors. So it'd be 120 plus 17. and you get 142 meters per second. And our observer is the plane, so it's asking which direction the bird's going. The bird still seems like it's going that direction. You don't have to do anything funky with the direction if they're going in opposite direction. The direction stays the same, you just add. But now we're going to look at the plane and the car. So down here, the car is going in this direction at 32 meters per second. So the car is going in the same direction. So you end up subtracting the two. So you do 120 minus 32, and you get 93 meters per second. Now the direction. When it's asking which direction the car is going to the plane. Well, the plane's going faster, right? So the plane's going to pass the car. So the plane is going to pass the car. So it seems like the car is going in this direction compared to the plane, because the plane is pulling away from the car. The car is going a whole lot slower. So to the plane, it looks like the car is actually moving backwards because the plane's moving faster. It's kind of like the same aspect of here. It looks like the person's going in the opposite direction because it's going faster than the person. You have the same aspect here. So it'd be 93 meters per second to the west. On this one, we do have some look at problems. Again, I highly suggest you to look at the whole entire test, all the multiple choice and all the free response. You never know what question might pop up, but we're going to give you 3 questions we highly suggest you to look at. But again, you would look at all of the questions. You never know, those multiple choice questions might pop up as well. So the first one to look at, it tells you to look at your Spaceballs question. So if you go to your test 3 over 1D motion, and you go to the Spaceball, so it says, the question reads, Spaceball 1 is traveling above the planet of the apes when Dark Helmet spots Lone Star Eagle 5. He hits the self-destruct button with his helmet, which forces him to evacuate Spaceball 1. Unfortunately, Lord Helmet was not able to reach the escape pod in time. Spaceball 1 begins to fall straight down. Begins. So that is a given. A given. Begins is a given. Because we're starting, right? So that means at the beginning, it wasn't moving. So your initial is 0 because it begins to fall straight down with an acceleration. So it just flat out tells you your acceleration. But the thing is down, right? It accelerates down and crashes on the Planet of the Apes with a final velocity of that. Units. So it says your final velocity is 1,889 meters per second. And it's asking for a couple of things. It's asking for 2 things. We have 2 unknowns. It's first asking for the time, and then it's asking for the displacement. So it's asking for time, and then it's asking for the displacement. There we go. We can look at our equations. So let's solve for time first. So we need an equation that has initial, acceleration, final velocity, and time. So if we look at our equations, you have final velocity equals initial velocity plus AT. Our final velocity is 1,889. And it equals our initial velocity, which was 0 because it begins, plus our acceleration, and we're looking for time. So that 0 can just go away, and we're left with 15.5, or 17.5, sorry. And then what you do to one side, you got to the other because you want t by itself, so you divide, and you get You put that in your hand to get a calculator, and you get that as your answer for time. And then it's asking for displacement. So again, so now you can add time into the mix. So we can use this equation, 1/2 VF plus VI plus T. So VF was 1,889. Oop, no way. 89. Our initial was 0, and our time we just figured out to be that. So now you just multiply all that. 9 plus that. And you get... Whoops, nope, you don't get that. Helps if you actually plug it in your calculator right. Always double check. Let's try that again, shall we? Erase. Thank you. So we get this big number. I was like, that number is not big enough. 3 meters. So there we go. And then it talks about, there's your Spaceball one that talks about your He-Man. So let's go talk about He-Man. So Skeletor was taking his pet Panther for his normal daily walk. Panther sees He-Man, and he takes off running. He-Man is, and it's starting to give you your givens, and it's giving you 25.2 meters away, and it takes Panther 5.3 seconds, so that's your time, that's your displacement, to get there. What is your average speed? So what is your average speed? Erase. So that's going to be your distance. So we're looking for, our unknown is speed. We only have one speed equation. Speed equals distance divided by time. So it's just 25.2 divided by 5.3. 25.2 divided by 5.3 is 4.76 meters per second. So that one wasn't that bad. And then it's talking about your students traveling. So this is the one that a lot of students had trouble visualizing. So it says students are jamming out and started their road trip on the 21-mile marker. So 21-mile marker. So that is your initial position. And then it says it's traveled, and they traveled all the way to 147-mile marker. They realized, and that took them 2 hours to travel. And then they realized she forgot her homework, so they had to go back. And then the homework was actually at the 12-mile marker. Or not home, sorry, CTC, but at the 12-mile marker. And it took them about 120 minutes to get there. So this is going to be your final position, because this is where we started and that's where we ended. And it's going to ask for a lot of things. So the first thing is going to say, what is the total distance? Remember, total distance is you're just adding up all the distance you traveled. So it have to be the total distance. So for total distance, we know how far they traveled here and how far they traveled here. To do that, you're just going to do 147 minus 21. So this whole entire track they traveled 126 miles. So that'd be like D1, 126 miles. Then we need to figure out how far they traveled in this section. So again, you would just do, because we started at 47-mile marker, just subtract it by 12. And you get to 135. So that would just be D2, because you only did 2 tracks. So total distance is you're just adding it up. So you do 126 plus 135. And so you traveled 260 miles in your first little, that's how far you traveled. So like in your car, if you had like little mile marker in your, like the little, in your car, how it tracks how much miles you moved, it would tell you you moved 161 miles. Now displacement. Displacement has an equation. It's your final minus initial. So your final mile marker was 12. Your initial mile marker was 21. So you just do 12 minus 21. And that gives you a -9, which makes sense because you had to go past where you started to go to CTC. So let's say you started at home, you drove, you realized you forgot your homework, so you had to drive all the way back to CTC, which is past your home. So this right here, come on. This right here would be your displacement. Now, it wouldn't be at an angle, it'd be straight. I just had to draw it that way so it would, so you could see, but that would be your displacement. Now, next part, it asks for your speed. Now, remember, speed is distance over time. Distance, we just figured out. Distance is 261. Time, we have to take both times into consideration. So we need to convert our minutes to hours. We don't want minutes. Minutes needs to go down the bottom. We want hours. So for 1 hour is 60 minutes. So we just do 120 divided by 60, and you get it for 2 hours. So it took 2 hours there, 2 hours there. So your total time was 4 hours. You just take your total distance divided by, let's try that again. Divided by your total time, and your speed was 65.25 miles per hour. So good, they were going the speed limit. Now your velocity is your displacement over total time. Your displacement was -9. Your total time was 4. So you do -9 divided by 4, and you get a -2.25. Again, miles per hour. So that's why it's called a speeding ticket, not a velocity ticket, because direction matters for velocity. So there's all the little hints for Unit 3. Hopefully you have happy studying. If you have any questions, just let Miss Verona or Miss Heath know. Have a wonderful day. Bye!